so they should be able to understand what we're talking about. And let's do a share screen. Can you see my screen? Yeah, good. Is lecture 27. So last time we completed the discussion about the weak interaction and the Weinberg-Salam model of the electroweak interaction and the hypercharge. And there is still one thing which is missing, which is the masses. So if you remember, we had, in order to get the symmetries in the SU2 left times Y1, U1 Y, then we had to assume that the gauge bosons are massless. Now we know that they are not massless. They have masses, so we need to find a way which will be consistent with everything that will introduce masses. That's called the brute Englert Higgs mechanism, which we will derive that in several steps. So we'll start to derive today, but I think we will not finish the derivation today. So there are two problems that we're trying to solve, right? One is that the gauge bosons, right? The first is that the gauge bosons, the W plus minus and the Z are massive. And if we try to give the mass, that this automatically breaks the gauge symmetry, right? The local gauge symmetry. And then within the standard model, there is another problem, right? Because we said that the left and right-handed fermions have different charges for the weak isospin, right? And different hypercharge, right? Which means that if we put fermion masses, they also break this gauge symmetry, right? The isospin and the SU2L symmetry. So we need to find a way to give them the fermion masses which will not break the symmetry. By the way, before I begin, are there any questions about what we said last time? No. So we said the problem one is the gauge bosons have masses, and the second is that the left and right-handed fermions have different couplings, or different charges. Just for the weak isospin or hypercharge, which means that the fermion masses breaks the symmetry. Now, so historically, you know, the Weinberg and the Glesio came down with this idea back in 1961. They had no solution to this problem. And then in 1964, Brute, Englert, and Higgs came up with the model. And as we're going to see, the model actually gives a prediction for a new particle, which is, of course, the Higgs boson, which was found later on. And it's now an essential part of the standard model of particle physics. Now, the idea of a hidden or broken symmetry, right? This is, I kind of mentioned it at the end of the last lecture. I mean, you know, in physics, we're searching for symmetry. It's beautiful, it's nice, you know, Newton's law, Coulomb's law, they're symmetrical. But there is something that breaks the symmetry, and we know that, right? You know, for example, in solid state physics, right, the essential forces are Coulomb forces. But although the Coulomb force would have a spherical symmetry, we hardly see any spherical crystals. Right? There is something that breaks the symmetry there. Same we can say about the Earth, right? It's not completely rounded. There are some things that break the symmetry. So, you know, something breaks the symmetry. Now, for our purposes, despite the fact that the Lagrangian is symmetric, the ground state of the system does not have to be symmetric. Let me write it down because this is a non-trivial statement. Despite the fact that the Lagrangian is symmetric, the ground state does not have to be symmetric. In fact, when you think of it in physics, we look for symmetries. We don't look at the ground state. We look for states which are excited, so they are above the ground states. But in order to get things proper, because I don't expect you to know essence of quantum field theory, and we are working in the frame of quantum field theory, let's state things in an ordered way. So in the framework of quantum field theory, right, if we look at a scalar field, right, what is a scalar field? We must remember that. What is a scalar field here? We said that the scalar field phi, right, is a function of space and time, right? And it obeys some equation of motion. Right? Can be the Klein-Gordon equation, can be the Dirac equation, right? Now, the equation essentially describes some dispersion relation, right, of a free particle. And we get to this equation by the Lagrangian. Now, all these equations always have a trivial solution, right? All possible equation of motion. We can always have phi equal to 0. That's a solution to the equation, right? There is a trivial solution. Right, phi equal to 0. It can be a psi. I write phi because it's a simple scalar field, right? Now, this solution, we call it the ground state, right? So this solution is the ground state, right? Right. Of course, it has the lowest energy. Right. Right. Now, here comes a crucial difference between quantum field theory and quantum mechanics, right? In quantum field theory, we interpret this state as having no particles at all. So that's why we call it vacuum state. Right? In quantum field theory, we say that there is a particle, it just doesn't have any energy, right? Or it has the minimum energy that can have based on Heisenberg's uncertainty principle, right? But in quantum field theory, we simply say that in this state, there are no particles. Right? So we call it the vacuum state. Right. Now, around this state, we do perturbation, right? We are interested in particles. So we do perturbation that treats a small number of particles, right? So the first quantum excited state is a state that represents a single particle, right? With a specific momentum. Second excited states represent two particles, right? So around this state, we use perturbation theory. basically that's for small number of particles. Right. So the first quantum excited state represents one particle. Right. With a specific momentum. Right. Second excited states represents two particles, etc. Etc. Now, okay, that's a general picture, which is true in quantum field theory. You learn that in quantum field theory course. Now, what happens? We're going to do the following things to the Lagrangian. We're going to add a self-interaction term. So now, apply that. Or not apply that, right? It's not applied. This is look at this picture under the following conditions. Right? Look at the following picture. That's more precise. Look at the following picture. So let's add to the Lagrangian a self-interaction term. Add self-interaction term to the Lagrangian. Right. What happens in this case, right? We say that the particle is no longer free. It's not a free particle, but it has some potential of the self-interaction. The particle is no longer free, right? But is inside the potential of the self-interaction. Now the potential does respect the initial symmetry of the Lagrangian, but its ground state can break the symmetry. It respects the initial symmetry of the Lagrangian, but its ground state will break its symmetry. Now what I'm going to show you is going to happen is that this situation, this picture, is going to lead us to a mass term of the different particles. We're going to gain masses for free, nearly. And it will also give us predictions that can be tested experimentally. This will lead to mass terms. For the different particles involved. And to testable predictions. Okay, this is the prescription. Now let's work at the details one by one. Questions? It's going to be a little bit technical, so I'm going to derive it in several steps. We'll have like 4 or 5 steps, which we're going to derive until we get to the full picture.
So
Yeah.
Maybe one question. You started with an example of a Coulombic force, which is a spherical symmetry. Continue by saying that lattices and crystals are not like that. But
yes.
Why actually you expect that this will follow the same symmetry? Do you have an example of such a case?
If I have an example, yes. If you think of, if you go above a certain size, then yeah, a certain energy level, then yes. If you think, for example, of a drop of water, and you put it in free space, it will be fully spherical symmetry, right?
Yeah.
Right. There are other examples. Actually, I'm not so expert in solid states, unfortunately. Let me think.
What drop of water? It's a question of surface tension.
Yeah, and what the surface tension comes from? This is exactly coming from Coulomb potential, right?
Yeah, but just because it's stopped to be symmetric, it's just on the surface, because it's not surrounded by other atoms, then you get the net surface tension.
Okay, I wouldn't argue with you because I'm not an expert in that. I think I wrote down some example here. Let me go back to that example. Another one, okay, that's an example of a spontaneous symmetry breaking. Let's wait with that. I'll get back to you later on with that.
Okay.
I don't think it's really matter for what we're going to say right now. I just want to give you some idea that it's not the first time in physics that we're seeing these symmetrical states which appear to be non-symmetrical. Okay, so let's start by deriving the mechanism. So what we're going to do now is symmetry breaking for real scalar field. This is we're still a few steps before we're going to do the real standard model. But to give you the feeling of how it's going to work, symmetry breaking for a real scalar field. So let's assume that we have a real real scalar field, so a simpler scalar field, and we're going to put a potential V phi, which is 1/2 mu squared phi squared, and then I'm going to add another term, which is plus 1/4 lambda phi to the 4. So the Lagrangian L, right, 1/2 d mu phi minus V of phi, right, 1/2 d mu phi minus 1/2 mu squared phi squared minus 1/4 lambda phi to the 4. Nothing special, right? What is this term, the first term? This is something that you should know by now.
Kinetic term.
This is the kinetic term. Very good. Right, this is the kinetic term of the field phi. What is this term? 1/2 mu squared phi squared.
Mass.
This is a mass, of course. And we have a new term, which what would this term represent?
Is this the interaction?
Exactly. This is a self-interaction term, right? Very good. So that means that our field, self-interaction, self interaction. That means that our field phi, right, can have a vertex, a 4-dot vertex, which coupling of minus 1/4, right? We have a self-interacting scalar field, right? Nice and easy. Now the vacuum state, right, is the lowest energy state of the field, right? And this should correspond to the minimum of the potential. So from that, let's write it down. Vacuum state, that corresponds to minimum of the potential. Right. That means that if we want the potential to have a finite minimum, that automatically means that lambda must be greater than 0. Right? Because if lambda is negative, then if we draw the potential, right, it will go to minus infinity for certain values of phi. Right? When phi goes to plus minus infinity. Now we have two options really. So option number 1 is that mu squared is greater than 0. Right? So if mu squared is greater than 0, right? Then if I draw the potential, right? So this is positive, this is positive. So the potential, right, phi and v of phi, right? The potential would look something like that, right? We'll have a minimum. It's a quadratic function. It would look something like that, give or take, right? So the minimum would be at phi equal to 0. That's where the minimum is, right? And if this is the case, then the Lagrangian we have really represents a scalar particle with mass mu and 4-point self-interaction term, exactly what we have here. But we can think of a second option. What if mu squared is smaller than 0? Right? Remember, this is how the potential looks like. This is going to be negative, and this is going to be positive, right? Lambda has to be positive, right? In that case, right? That means since this is negative, this is going to be positive. We cannot. This is no longer going to be associated with a mass. We cannot interpret this as a mass anymore, right? And if we look at the potential, if we draw the potential, okay, this is phi and this is v of phi, then the potential now would look something like that. We have two minima, right? Plus v and minus v, right? Where the minima, still leave it here, right? Phi is plus minus v, which is plus minus square root of minus mu squared over lambda. So it's clear to everybody? This is just a choice of a sign from mu squared. So we no longer have a mass term, right? And the lowest energy state does not occur at phi equal to 0, but rather at phi equal plus minus v. All right. In this case, we say that the field has a non-zero expectation value. Now the Lagrangian is still symmetric, right? The Lagrangian is symmetric because if we change phi to minus phi, nothing happens to the Lagrangian, right? Lagrangian is here. Lagrangian is symmetric under exchange of phi to the minus phi, right? But physically, right, the vacuum state can be only in one of the two possibilities. Either it's in a plus or in a minus, right? So L is symmetric under phi goes to minus phi.
Is there
But,
is there a simple example that doesn't require an imaginary mass?
Wait. It's not a mass. Now we have to interpret this in a completely different way. We'll get to that. Right. Yeah, the example. There are examples. That's what I was looking for. There are examples. Wait. Let me finish that, and then we will say it. Right. Now the vacuum state can be in only one of the two possibilities, right? So the vacuum state can be either in phi is plus v or phi is minus v, right? Now the choice of which one, right? That's going to break the symmetry of the Lagrangian, right? And when this happens, then it's called a spontaneous symmetry breaking, right? So the choice of which state which is the real vacuum state, which is the physical vacuum state, this is called spontaneous symmetry breaking. So the analog example is if you think of a ferromagnet that is cooled below the Curie temperature, right? Then, above the Curie temperature, the spins are random. But if you go below the Curie temperatures, the spins are going to align in the same direction, right? But you don't know in advance which direction it's going to be. All right. Now, question? Did this answer your question? Okay, can I proceed? You're very quiet. Are you muted? It's okay. Can we proceed?
Yes.
Okay. Now, of course, without loss of generality, let's take the vacuum state to be in the positive direction, right? So assume, without loss of generality, assume right, that phi is in the plus v. Now, this is the ground state, right? So this is the vacuum. Now we want to get particles, so we want to get excitation about that. So let's consider a perturbation, but the word perturbation is a bit misleading here because it doesn't have to be a small perturbation. It just have to be a perturbation that still stays here in this positive half, right? So excitations of the field, ground state. Excitation of the field describe particle space. Right. We can write it down as phi of x is v, which is fixed, plus another field eta. of x. I'm simply shifting now, right? I'm breaking the symmetry in the sense that I'm shifting the field from, its 0 point to the 0 being at phi equal to v, right? So I can express now the Lagrangian rather than in terms of phi, in terms of the new field, eta, right? And v, which is constant. So I take the Lagrangian, which is written here, and I simply plug in, every time I see a phi, I plug in v plus eta. Remembering that v is constant, so I don't need to take its derivative, right? So I end up that this Lagrangian, right, this Lagrangian, I can write it down as L is 1/2 d mu eta, sorry. Minus 1/2 mu squared v plus eta squared minus 1/4 lambda v plus eta to the power 4. Now, rather than v, no, actually, I don't. We still have the mu squared here, but I don't need the mu squared because I know that the minimum of the potential is right here. So mu squared is minus lambda times v squared. So I can write down mu squared to be minus lambda v squared. And then I can further simplify the Lagrangian, and I get the Lagrangian is 1/2 d mu eta minus lambda v squared eta squared minus lambda v eta cube. I did the algebra at home, so I'm just giving you the final result. You can practice it. Minus 1/4 lambda eta to the 4 minus plus 1/4 lambda v to the 4. Simply plug it in and open. Some terms will cancel. Okay. So we have one term that is proportional to eta squared, which is this term. So we can interpret this term as a mass of the eta field, right? So this is interpreted, right, as a mass of the eta, which means that the mass of the eta field is square root of 2 lambda v squared. Or again, using mu squared is minus lambda v squared, this is just square root of minus 2 mu squared. Which means that this Lagrangian that we have here, right, is describing really a massive scalar field, right? Which, okay, so the Lagrangian right, describes a massive scalar field. Eta. Right. Now we say that the mass was created or discovered by the symmetry break. Mass was created or discovered by breaking of the symmetry. now when you think of it a little bit, you realize that we get to this mass term because what we did at perturbation, right here we had the perturbation, and we required that the we are near the minimum of a parabolic potential well. Essentially, this is the standard thing we do in physics, right? We take any potential and we say, okay, we can approximate it as being a parabolic near the minimum. Right. Again, it's a similar thing. Similar analogies exist in other branches of physics, right? Phonons obtain their effective mass because being near the minimum of a parabolic potential. Now we still have some other terms here, right? So we have this, triple potential and a quadratic potential, right? So we can interpret them or identify them as triple and quadratic interaction terms. So we can interpret these terms as being triple term, right? So something like that, right? Eta, and eta, right? It's a coupling constant of lambda v and a quadratic one. Eta. So we'll have a 1/4. Happen? So 1/4 lambda. Right? Of course, the last term is just a constant. Right? This term here is just a constant, so it has no real physical meaning. Now remember, we didn't really do anything. We just took the Lagrangian and did a small algebra, right? So it's the same, the Lagrangian that we have here, right? It's the same Lagrangian that we had originally. We just added this term, put the minus sign in front of the original mass term, and we simply express it in a different way, right? We just express it around a new minimum, around phi equal to plus v. And of course, the field of interest to us is going to be this eta field, because it's going to describe changes around this, or excitations around this new vacuum state. Okay? It's a small algebra with a big physical interpretation. Any questions? You just have to have one good idea. That's enough to get you a Nobel Prize. All right. Yeah. Now, okay, let's proceed on. So the next thing I'm going to do is a global symmetry breaking of a complex scalar field. So I told you that we're going to have several steps until we get to the real standard model. What happened? I lose my. Okay. Oh, it's back. Yeah, I have a weak. We have a weak connection, which can go wrong. So let's do now a global symmetry breaking of a complex scalar field. Going to raise the level of complexity. So in the previous example, we spoke about the real scalar field. So now let's talk about a complex scalar field. So let's write down phi as 1 over square root of 2, phi 1 plus I phi 2. So we have now two real scalar fields. Right, and phi is a complex field. So the Lagrangian L, right, d mu phi star d mu phi minus mu squared phi star phi minus lambda phi star phi squared. Now we're going to essentially repeat the same calculation as we just did. So, the first thing is to ensure that the Lagrangian has a finite minimum. Then we require that lambda is greater than 0. Now, just by looking at this Lagrangian, right, it's clear that we have an invariance under global U1 phase transformation, right? L is invariant under phi goes to phi prime E I alpha phi, right? Because obviously phi prime star phi prime is phi star phi. Should be quite straightforward by now. Now again, similar to what we did for the real scalar field, we have two options. If mu squared is greater than 0, then the minimum of the field occurs when the minimum of the potential, occurs when both fields are equal to 0, right? So for A, right, mu squared is greater than 0, then if I have to draw that, let's try to draw that with my phi 1, phi 2. This is the potential v phi. So it should look like a ball, basically. Some sort of a ball around here, right? So the minimum is that phi 1 equal phi 2 equal to 0. Of course, the interesting case is what happens if mu squared is smaller than 0. And again, if I have to draw, then what we get is something that looks like, Mexican hat of some kind, right? What you understand from my lousy drawing, what's going on here? So it looks like a sombrero in some sense. So we have basically an infinite set of minima. Right, which are defined by 2 phi star phi, which is just phi 1 squared plus phi 2 squared, is minus mu squared over lambda. And we call this v squared. Right, so everything around here the minima of the potential. Of course, the physical vacuum state will correspond to a particular choice of point in this circle. And when we do that, we have to break this global U1 symmetry of the Lagrangian. Right. Physical vacuum state corresponds to a particular choice or particular point on the circle. Right, which means that this breaks or breaking global U1 symmetry. Right. From here, it's quite obvious what is the symmetry of the Lagrangian, right? Since we can rotate this sombrero, this is the symmetry of the Lagrangian. So again, right, without loss of generality, we're going to choose the vacuum state to be in the real plane. So, we're going to put this to be the vacuum state that we choose right here. So we choose phi1, phi2 to be equal to V and 0. That's our choice. Once we made this choice, we broke the symmetry, right? And then we do like we did in the previous case of the real field, right? So we expand the field around this vacuum state. So we expand the field. By writing phi1 of x is V plus eta of x. Phi2 we don't need to expand, right? So this is in this phi1 direction. Right? And the phi2 we don't really need to expand, so we simply write it down as psi. Because it's going in that direction. So overall, we write down phi to be phi of x, right? 1 over square root of 2, V plus eta of x plus I psi of x. So psi is a radial perturbation. So sorry, eta is a radial perturbation. And psi is a perturbation in the imaginary direction. Right. So again, now it's just a matter of simple algebra, putting all that back in the Lagrangian, and using the fact that phi star phi is just 1/2 V plus eta squared plus psi squared. And again, mu squared is minus lambda V squared. And then we write the Lagrangian. Right, L to be 1/2 d mu eta plus 1/2 d mu psi minus lambda V squared eta squared minus V interaction of eta and psi. For V interaction, of eta and psi is minus 1/4 lambda v to the 4 plus lambda v eta cube plus 1/4 lambda eta to the 4 plus 1/4 hope that I'm not mistaken, lambda psi to the 4 plus lambda v eta psi squared plus 1/2 lambda eta squared psi squared. Now, you get it by simple algebra, right? You just, as we did with the scalar field, you just plug in this, expansion of phi, right? This expansion of phi, you just plug it into the Lagrangian, and you open up all the terms, and that's what you get. Modulo some typo that I got, but I don't think so, because I checked it. So you end up that there is only one term, this term, which is quadratic in the field eta. It's the only quadratic term. All the other terms are not quadratic. Right. And so we identify this term as the mass term of the eta field, right? So that means that we write down that half m eta squared is lambda v squared. Now there is no quadratic term in the field psi. So the field psi is interpreted as a massless term. No quadratic term in psi. So that is mean that psi is massless. Everything else, which means all the terms which are inside this interaction part of the potential, right? Everything here, right? All these terms represent interaction between the fields, right? So triple and quadratic couplings of the fields eta and psi. Right? So it's a triple quadratic, 4-point vertex, etc. of these fields. Now, so we got one, the excitation of the massive field eta, right, as we had previously, right? So this is the field eta, would go in here, right? So these excitations are in the direction where the potential is quadratic, right? The first order, of course, quadratic. Now, the particle that describes the massless scalar field, psi, right? It's an excitation in the perpendicular direction, right? So the psi would correspond to excitations in this direction, where the potential is not changed, right? I start from the minimum point, then I try to shift it a little bit. The potential doesn't change. And I get a field which is massless. There's no masses to these fields in this direction. Okay. Now this massless particle or field, right, scalar field, you might have heard the name. Does anybody want to guess? No. It's called a Goldstone boson. So the field psi, the massless scalar field psi is called Goldstone boson. Is that clear? What happened so far? Getting slightly more complicated, but I told you we have to have to derive it in few steps. So now let's go to the next step, Now we're actually going to speak about the BEH mechanism, the brute Englert-Higgs mechanism, still not in the context of the standard model. What will be the next level of complexity? Anybody want to guess?
Vector field?
No. We had a breaking of a global symmetry, right? But what do we have in the standard model? We have local gauge symmetries, right? So that's what we're going to speak about now. And that's called the brute Englert-Higgs mechanism. Brute Englert. For short, it's the Higgs mechanism, right? So we have, in this mechanism, we have a spontaneous symmetry breaking of a complex scalar field, the same complex scalar field we had previously. But now the spontaneous symmetry breaking is not of a global gauge symmetry, but of a local gauge symmetry, the same one that we learned previously. So talk about spontaneous symmetry breaking of a complex scalar field is the potential V of phi, and it's the same potential, mu squared phi squared plus lambda phi to the 4. But now of a local gauge symmetry, spontaneous symmetry breaking, or SSB, right? Spontaneous symmetry breaking of a local gauge symmetry. Which is given by a local gauge transformation. Right. So let's start with the simplest one, which is the local U1, right? So, for example, this is not yet the standard model. So the example I'm going to give to show you what happens is the local U1 transformation, which is phi of x goes to phi prime of x, which is EIG chi of x, phi of x. Now remember, G is the coupling constant, right? And the phi has a charge of 1, right? It doesn't appear directly in the exponent. Right? For electric charge, we had a QE, right? E is the coupling constant, Q is plus minus 1 for protons and electrons. So now we have to apply everything we learned previously, right, about local gauge symmetries. So in order for the Lagrangian to be invariant under the local gauge transformation, right, we need to replace the derivative with what? It's what? What did we do?
We added a term to the derivative.
What did we do to the derivative?
Added a term.
Right. We replace it with a covariant derivative. Very good. We replace the derivative with a covariant derivative. right? D mu goes to d mu, which is d mu plus ig b mu, right? So introduce a new gauge field, right? B mu, which by itself has to transform in a certain way, where B mu, right, the gauge field, goes to B mu prime, which is B mu minus D mu chi of X. So just in the case that we did previously, right, for the Dirac-Lagrangian, for example, right, required local gauge invariance implies that there exists a local new gauge field, right, which has a well-defined gauge transformation properties. So the requirement for local gauge invariance implies the existence of a new gauge field with well-defined transformation properties. So the combined Lagrangian, right, of this complex scalar field phi and the gauge field B, we get the Lagrangian is L is minus 1/4 F mu nu plus D mu phi star E mu phi minus mu squared phi squared minus lambda phi to the 4. F mu is the kinetic term of the field. Similar to what we had previously, F mu nu would be defined as D mu B nu minus D nu B mu. Just to make sure that we have a kinetic term for the field as well. Now, note that we did not put any mass term for the field, because if we were to put a mass term for the field B, it would break the gauge invariance. Which is exactly what we had previously, right? And I told you back then, okay, forget about the masses of the field. Right? But now, I just mentioned that. The same thing we had before, but now we have a different interpretation. We added up this quadratic term, sorry, the term for the phi to the 4. And we're now proceeding the same way as we did previously. So just put it down, note that. So now for mu squared smaller than 0, the symmetry now breaks, right? For mu squared smaller than 0, then the symmetry breaks. Right? Which means that the vacuum state is degenerated. And the choice of the physical vacuum would mean that we have to have a spontaneous break of the symmetry. So as we did previously, right, we just choose the vacuum state. We choose the vacuum state. Right. Phi 1, phi 2 is V and 0, exactly what we did previously. This is the spontaneous symmetry breaking. or SSB. And then we expand the complex scalar field around this new vacuum state. Put everything here inside the Lagrangian. And when you do that, you get that the Lagrangian now will become 1/2 d mu eta minus lambda v squared eta squared plus 1/2 d mu psi minus 1/4 half mu nu plus 1/2 g squared v squared b mu minus v interaction, which contains all the interaction terms, plus g v b mu times d mu psi. So again, this is just algebra, right? Just plug in everything into the Lagrangian and that's what you get. Now, I strongly urge you to do that at home. Don't trust me. Now, similarly, the V interaction, which is a function of eta, psi, and now the new gauge field V, right? This will have all the 3- and 4-point interactions, right? Of these 3 fields. Eta, psi, and V, it's going to be quite long and complicated. All 3, 4 point interaction terms of the field. Right, the fields do interact with each other. Now, what do we have in the Lagrangian? Let's do it. So the first 2 terms, what is that?
Kinetic term?
Sorry?
Kinetic term.
The first 2 terms represent the field eta, right? So we have the field eta. It's a massive field, right? So let's call them terms 1 and 2, 3, 4, 5, 6, 7. We have 7 terms in the Lagrangian here. There are many more because the interaction contains a lot of terms. So terms 1 plus 2, right? That's massive scalar field. Right, eta. The mass, half m eta, is just lambda v squared. Again, similarly to what we had previously, right? The mass of the field eta came from the breaking of the symmetry of the Lagrangian. Right? M eta originated from breaking symmetry of the Lagrangian L. Now we have a third term. What is this term? What is term number 3?
The Goldstone mode.
This is the Goldstone boson, right? This is a massless, right? There is no mass term for this one. So term number 3, right, is the massless scalar Goldstone boson. Now, okay, what about terms 4 and 5? So what are these terms? What appears in these terms? What field appears in these terms?
Gauge boson.
Right, this is the gauge boson, right? This is the kinetic term. Number 4 is the kinetic term for the gauge boson, right? And what is number 5? That's a mass term for the gauge boson, right? But this is a new term, right? We did not have it previously, right? We did not have it when we had the breaking of the global gauge symmetry. Now with this new term, right? This term here, right? This is a new term that appears because of the breaking of a local symmetry, right? This is the Higgs mechanism, right? We obtain a mass term by breaking a local gauge symmetry. So 4 and 5, right? This is the vector field V mu, right? Term number 5, right? Means that the previously massless gauge boson B mu got mass, right? And half G squared V squared is 1/2 M P. This came from the covariant derivative. It originated from the covariant derivative. Which means that it's really a result of a local symmetry breaking. Right, in essence, this is the Higgs mechanism, the local symmetry breaking, as opposed to global symmetry. This is the Higgs mechanism. Okay, it's not bad. We got somewhere, but it's incomplete. We seem to have two problems, right? What about this last term here? This term, number 7. What does it represent? What do you see here? I'm seeing here a direct coupling, right, between the Goldstone boson Xi and the vector field B, right? Term number 7 represents a coupling. So there is some interaction between the Goldstone field Xi, right? But this is a scalar field, which is spin 0, and the gauge boson B, but this is a vector field, right? Which has also spin 1. So it's not clear. I mean, that's okay. It cannot be physically that you have a vector field with spin 1 interacting directly with the scalar field of spin 0. So that's one problem. So, however, term number 7 represents a direct interaction between Goldstone boson. And B mu. Cannot be physically. Then the second problem is that if you look at it carefully, you realize that the original Lagrangian had really 4 degrees of freedom. We had this scalar field phi. You can think of it as phi 1 and phi 2. And we had the 2 polarization states of the massive field B, which was introduced. And when the gauge boson became massive, we had an additional state, right? A longitudinal polarization state, the same as we had with the Procca equation. Take you back a few lectures ago. So we somehow added a degree of freedom. Addition of the mass term to B mu added an extra degree of freedom. Which doesn't make sense. So what do we do with these problems? So the way out is to realize that the fields that we have in the Lagrangian are in fact not the physical fields. The solution is to realize that the fields that appear in the Lagrangian are not physical fields. Right? So in fact, we can eliminate the Goldstone term from the Lagrangian by noting that we have, so everything that involves in the Goldstone, let's picture it in some color. What color should I choose? So the Goldstone, right? We have the kinetic term, right? We have the interaction term, and we have the mass term of the Goldstone. So if I take these 3 terms, 3, 5, and 7, I can write down term 3 plus 5 plus 7 1/2 d mu psi plus gv b mu d mu psi plus 1/2 g squared v squared b mu. I can write them down as 1/2 g squared v squared b mu plus 1 over gv d mu psi squared. Just simple algebra, right? But now I can make a gauge transformation. Now gauge transformation. B mu of x, right? Go to B prime mu of x, which is just B mu of x plus 1 over gv d mu of psi of x. Right. And this can work out because what we have here in the parentheses is a derivation of a derivative of a scalar function. So we can simply gauge it out without having any effect on the physics. Right? it's essentially making this transformation. Remember, where did I get this B, right? B is just this field that I get by adding this field to the Lagrangian to keep it symmetric. When I had this transformation e to the I g psi, high. Right? So it's essentially, this is equivalent of writing down, of choosing a gauge where chi is minus psi over GV. This has a choice. This is a name which is known as the choice of a unitary gauge. This choice is known as unitary gauge. So the corresponding gauge transformation would be, let's put it down, phi of x goes to phi prime of x, which is e minus I g phi of x divided by gv, phi of x, so it's e minus I psi of x over b, phi of x. And when we do that, we can write down the Lagrangian where L is 1/2 d mu eta minus lambda v squared eta squared minus 1/4 f mu nu plus 1/2 g squared v squared b mu prime v mu prime minus v interaction. It's the same Lagrangian. Right, this Lagrangian is the same as the Lagrangian we had here. Just made the transformation from b mu to b prime mu. But when I did this transformation, all the terms that contain the psi, the Goldstone boson, just completely disappeared. So there goes the extra degree of freedom. So the degree of freedom of the scalar boson was in fact replaced by the degree of freedom that corresponded to this longitudinal state of the massive vector field b mu, or b prime mu, sorry now. So let's write it down, right? All terms that contained psi disappeared. So solving the extra degree of freedom problem. Right. We say simply that the Goldstone boson was eaten by the gauge field. Right. This is what happens in the unitary gauge. So the degree of freedom of the Goldstone scalar was replaced by the degree of freedom of the correspond to the longitudinal state of the massive vector field B. So simply say that the Goldstone boson was eaten by the gauge field.
Can I ask a question, Asaf?
Yeah, of course.
This is a very neat and elegant mathematical trick, but nature, if I understand correctly, doesn't choose a gauge, right? It's invariant under gauge transformation, so any gauge must be equally valid.
Yeah.
So why is this? I mean, okay, it's a mathematical trick, but why? So does this Goldstone mode exist in nature, or like?
We're still not talking about the standard model. We're talking about the general U1 local gauge symmetry.
But given a system where this Lagrangian describes the system, right?
Yeah. It's again, it's a local choice of it's a choice of a vacuum state essentially, which breaks the symmetry. You would get it anyway. You just have this extra degree of freedom that you need to get rid of. You know, when I said it, the picture I have in mind, we're going upward, is this picture here, right? This is the thing, right? It's symmetric, you know, along rotation. I mean, this U1 symmetry, what does it mean? Basically means that if you take it and you rotate it, it's symmetric. It doesn't matter where you are. Now you break the symmetry, right? I break the symmetry by choosing that the real vacuum would be here, right here, and not here. Okay, now it doesn't matter where I choose it, right? I could have chosen it here. Then simply the direction of the Goldstone boson would be in that direction, not the other one. So it wouldn't make any difference. And yet this is still not the standard model symmetry that I'm going to break.
I understand the point of the symmetry breaking. What I'm asking is, so given a system where this Lagrangian, you know, governs the system, can you excite this Goldstone mode, or does it not exist because you could gauge it away?
I would not. The Goldstone mode would always be in the direction where the potential is not changed. That's why it's massless.
You can still excite it in a, you know, some.
No, I'm trying to excite it, but the potential is not changed in this direction. Well, the eta field, my definition is that the eta field I'm always choosing along the direction where the potential does change.
Well, I understand that it's a radial and a tangential or angular field. I understand that point. What I'm asking is, you were able to mathematically make it disappear. Does it mean it doesn't exist, or does it mean that like you can just write it in a more elegant way, but it's still somewhere hidden inside, you know? And then if I actually build this Lagrangian, you know, in a quantum simulator or whatever, I would still be able to measure the dispersion relation of this Goldstone mode, which is a massless, you know, omega proportional to k.
Well, yeah, but this is a mathematical game, right? It physically does not exist, right? It does appear in the Lagrangian, right? But it's just a way of presentation, right? Like we said that we started with the field phi in the Lagrangian, and then I switched to another field, eta, and I said that this is the real field in some sense, right? This is what we're actually measuring in the lab. I write the Lagrangian, I think now I understand your question. I write the Lagrangian, right, in terms of some fields, but when I do measurements, right, these do not correspond to the physical measurements I can do. I do not measure the field phi. I do measure the field eta. I do measure the B. Now, essentially, B is going to turn out to be the W and the Z bosons. Not here, but in the next level of complexity, right? But, you know, let me finish. I just need, I have like, let me finish that. And then since I'm running out of time, I have to finish that so that we will be able to finish on Thursday. So the Goldstone boson was eaten by the field. So it doesn't have any physical meaning. The two scalar fields, right? We still have two fields, right? One, we have this massive scalar field. So this is, right, the massive scalar field that we have here, right? Let's call it its real name, right? So eta of a massive scalar field. Right, it's called eta of x. And I guess you can guess what is the common name for this field. It's noted by age of x. So that's a Higgs field, or that's a Higgs boson. And B prime was got just by choice of a gauge. So I can simply write it down as B. So let's write down the Lagrangian. So if I do eta, I'm replacing it with an H, and B prime, I replace it with a B. Then we get that the Lagrangian is 1/2 d mu H minus lambda V squared H squared minus 1/4 F mu nu plus 1/2 G squared V squared B mu B mu. Let me write down the interaction term explicitly. That gives plus G squared V B mu H plus 1/2 G squared B mu H squared minus lambda V H cubed minus 1/4 lambda H to the 4. So the first two terms here, this is for the massive H scalar. This is for the massive gauge bosons, of course. Right, so we get the gauge boson, which now does have a mass, which is what we wanted. And these ones are interactions between the Higgs field and the gauge boson. Right, and this is self-interaction of the Higgs with itself. Right, so the H with the B, right, we have a term which looks like H B mu, so it would look like that, H B V is coupling of G squared V, and the second one is H squared BB, H B B, 1/2 G squared. And then we have the self-H interactions, right? So we have the H 3-point vertex, and then the 4-point vertex. H with coupling of 1/4 of lambda. Right, now the mass of the gauge boson, right? MB, what is that? Just GV. MB is just GV. This theory, right? It just relates to the strength of the gauge coupling and the vacuum expectation value of the Higgs field. We also have the mass of the Higgs field, M Higgs, right? It's just square root of 2 lambda V. So the vacuum expectation value V gives us the right scaling of the masses of both the Higgs and the gauge boson, right? They're both linear, proportional directly to V. So just final words, and then I'll answer questions. So we assume the local gauge symmetry, right, U1, which breaks the ground state of the potential of a complex scalar field, right? And as a result, what we got is that 1 degree of freedom of the scalar field was eaten, right, and then added to the gauge field, thereby obtaining a mass. The 2nd degree of freedom of the scalar field becomes a massive scalar field. And we know exactly what are the allowed interactions, right, between the massive scalar field and the gauge boson. And we also know exactly their couplings. Right. So assuming a local U1 gauge symmetry, which is broken by the ground state of the potential of a complex scalar field. We get 1 degree of freedom of the scalar field namely the Goldstone, right? Psi E10 added to the gauge field. Which acquires a mass. And then 2nd degree of freedom becomes a massive scalar field. And we know exactly the allowed interactions. The model defines exactly the allowed interactions. And the couplings. We don't have any more freedom. Once we know what is V, once we know what is, what else do we need to know? No, V and lambda we need to know to get the mass of the Higgs. But we know exactly what interactions we're going to get. Now, this is still not the standard model Higgs. This is just an example of a local U1 gauge symmetry, right, which is broken. Now, which symmetry do we have to break spontaneously in the framework of the standard model? Can answer. It's just what we saw previously.
The weak force.
L, exactly. The electroweak force. SU2L times U1Y. When we're going to get that, right? Here in this example that we had one scalar field, right? But in that model, excuse me for that, but in that model, when we're going to break, we're going to get 4 fields. 3 of them are going to get masses. This will be the W and the Z. One of them is going to remain massless. That's going to be the photon. As I'm going to show you, the masses are not going to be, well, we can see it from here pretty much. They're not going to be random. They're going to be related to each other. Once you know the mass of one of them, you'll know the masses of the other 2. Quite cool, isn't it? Very cool. So okay, so we will discuss that on Thursday. And then we will discuss how, in addition, the Higgs mechanism not only gives masses to the W and Z bosons, but in fact to the entire fermions. And then we'll discuss, once we understand that, we can discuss how it's been experimentally measured in the lab. The lab is, of course, CERN, in the ATLAS and the CMS detectors. What exactly was done there and how it was done. And that will pretty much get us to the end of the semester. I would be happy to have another tutorial, which I don't see when to put. So I might as well skip it, or I might just post it on the course webpage and I'll let you study it yourself. Well, there are a few bits and pieces that I want to finish about the particle detector. We should kind of close it up everything, which we're doing about how these detectors work and how they discover the Higgs. And that is going to be it. Now I started to think of your exam. Since this is the first time the course is given here, not exactly, I understand it was given from a few years ago by somebody external to Bar-Ilan. But it's the first time it's given by me, and you don't have the experience in past exams. I will not make it a very difficult exam, but I definitely will require you to show knowledge and understanding. Not so much memorizing. I don't expect you to memorize, but yes, to understand. Questions? Any questions? No? If not, no questions, you sure? I see some people left. No questions? Okay, then I wish you a great day.
You too. Thank you very much.